Can you hear me? Okay.
All right, so let's continue with our last talk of the day. But just before he starts, I'd like just to thank you, all of you, for coming here. I hopefully you enjoyed your stay. Okay, not just yesterday, but also today and during the talks. So thank you so much for coming. We plan to have this conference like every 2 years. So hopefully we'll continue in the next years and see many of you in 2 years from now. Okay? So, Jamerson, take your time and check the clock.
Okay, thank you, Ronaldo. Good morning, everyone. First of all, I would like to thank the organizers for the opportunity to give this talk here. And we will talk a little about neutrino masses and cosmological inflation in a B-L standard model extension. So this work is mainly based on this paper that was done with the help of Antonio, J. Wilson, that was 2 colleagues in my PhD, and under the supervision of Professor Carlos Pires. So this is the outline of this talk. I'll give you some quick motivation, talk a little about the seesaw mechanism and inflation. Also, I will talk non-minimal inflation and the unitarity problem that appears at some of these kind of models. We will perform some slow analysis and give you some quick conclusions. So, as motivation, as we see here, we have some results that comes from space-based experiments. We have the COBE collaboration. We have some the CMB sky map from WMAP, and we have some results from Planck. And what I want to tell you here is that with the increasing precision of these experiments, the cosmologists could be able to estimate the standard model cosmological parameters. In special, for the first time in history, we were able to estimate parameters related to the primordial universe. So when I say primordial universe, I'm talking about inflationary time, inflationary epoch. So I'll erase this part here. Basically, the amplitude of scalar perturbations, the spectral index, and the tensor to scalar ratio. So for the first time, we have trustable measurement of these parameters that is correlated to the primordial physics, to the primordial universe. So this works is based on two main goals. The first one is to propose a model that is capable to describe the measured values to these parameters, to these observables. And the second is, given these values, these measured values, can we constrain the parameter space of our model based on these measurements? So basically, this is the 2 goals of this work, and I will try to reach this at the end of this talk. So first, I will give you some hint into the inflationary paradigm. The inflationary paradigm was idealized by Guth as an accelerated expansion in the primordial universe. Was thought in that way in order to solve many inconsistencies of the standard cosmology, such as the flatness problem and the horizon problem. In order to achieve this accelerated expansion, the universe must be dominated by a constant or almost constant component of energy. Let's say the cosmological constant. In that case, the universe would reach a de Sitter expansion. Would reach a exponential expansion. When we see it in the optics of a field theory, we can imagine a scalar potential that has a flat direction in some regime of energy. When the field is rolling in that flat direction, it mimics a cosmological constant, so the universe expands exponentially, at least at this regime of energy. So basically, this is called the slow roll mechanism because of that, because the field, the Inflaton field, is rolling slowly a scalar potential. So in some given time, this slow rolling will break. Then the Inflaton field will reach the VEV, the vacuum expectation value. And at this moment, it will oscillate and decay into the standard model particles, reheating the universe, reaching the Big Bang evolution of the universe. So basically, this is how it's done, how it is applied, inflationary expansion in the field theory. But what does it have to do with neutrino physics? Just in the beginning, I said that we'll treat about the neutrino physics. Basically, as we have seen this through this week, the canonical mechanisms to give neutrino masses are the seesaw ones. The seesaw mechanism is based on simple arguments. First, we include a high energy scale. This energy scale is correlated with the lepton number breaking. And with that, we create a time energy scale that is linked to neutrino masses. So we have to introduce in our standard model a high energy scale. This is done basically by the introduction of new fermions and new scalars. For example, in the type 1 seesaw mechanism, we introduce 3 right-handed neutrinos, and we can introduce also a scalar singlet that is responsible for the break of the lepton number at high energies in order to produce these Yukawa Lagrangians. We can use as example also the type 2 seesaw mechanism, that in this case we introduce a scalar triplet in order to obtain this Yukawa Lagrangian. Here, this F field is the lepton doublets of the standard model. And of course, when the neutral component of this triplet and this scalar singlet, standard model singlet acquire VEV, we will trigger the seesaw mechanism, and the neutrino get mass accordingly. So the seesaw mechanism introduced in the standard model new scalars associated to high energy physics. Those are the basic components of an inflationary model. So why not to try connect neutrino physics to inflationary models? Many authors have this idea. This is not new. And what is basically done is to evaluate one loop correction, or a radiative correction, to the inflationary potential that is usually a quartic potential. So this is the one loop Coleman-Weiber radiative correction. Well, here, in the case of type 1 seesaw mechanism, of course, this is model dependent, but here we have the main contribution that comes from the Yukawa sector to the type 1 and type 2 seesaw mechanism. Here at type 2 seesaw mechanism, you can see that we have the contribution from the gauge sector, as we are talking about a triplet, a scalar triplet under the standard model symmetry, SU2 symmetry. So when we do this and we do the slow rule analysis, we can calculate the observables, the inflationary parameters that is measured by the Planck, and can compare these predictions to the observed Planck regions. Here we have these predictions. Each one of these lines was calculated varying the radiative correction. So this continuous line here are calculated to the number of E-fold indicated by Planck. So as we can see here, the radiative correction inflationary model does not really describe the favored region of Planck that Planck observed. So it's not a good model to describe the measured parameter by Planck. So we have to think in alternatives to describe inflationary, the inflation, okay? So what can be these alternatives? What can we think? What can you think to describe this inflationary time of the universe? Well, here we have the released comparative study of the Planck collaboration. And as you can see here, we have chaotic inflation, cubic inflation, chaotic quartic inflation is not a good model. We have also others candidates here, but the model that is right in the middle of observed Planck region is the model related to modified gravity. Here we have the Starobinsky inflation, that is a modification of the gravity sector. Okay, so Starobinsky-like inflationary model are just let's say the perfect candidates to describe inflation. This motivated some authors to propose alternatives with modified gravity to explain inflation. In particular, of some interest, there is the Higgs inflation, because of the simplicity of this proposal. We have, it was built by Bezrukov and Starobinsky, Bezrukov and Shaponikov, and they thought that the Higgs could actually play the role of the inflaton in the beginning of the universe. How they managed to do it? Basically, this 5 field here is the Higgs field, okay? Basically, they coupled this Higgs field with the rich scalar. So we have a non-minimal gravity sector. We have a non-minimal coupling between the Higgs and the rich scalar. As a main result, when we are exploring the high energy regime of this potential, we get a flat direction in the Higgs potential. So basically, we have what we need to perform inflation in this model. And as we can see here, those are the predicted values to the inflationary parameter, and they are, as we saw in the figure here, those are just in the center of the predictions of the measurements of Planck collaboration. So that's fine. That's a beautiful model. We can take the Higgs as the inflaton. Not so fast, because when we try to describe the measured value to the amplitude of the scalar perturbation, we have to impose this kind of constraint in the quartic coupling of the Higgs. But we know that this quartic coupling is related to the mass of the Higgs field. So it is not a free parameter. So let's suppose that is 10 to minus 1. So we must have a non-minimal coupling that is of order to 10 to 5. First, this is a really unnatural value to a coupling, but it's not the only problem. The problem is that when we couple some scalar with the rich scalar, we introduce a new energy scale in your model. This energy scale is associated to the loss of the unitarity in your model. This is the energy scale. Above this scale, your model, it's just like a cutoff, right? Above this energy regime, your model is not trustable. The problem here is that as in Higgs inflation, we have this size for the non-minimal coupling, we have that this scale of energy is too low. So as inflation happens at the higher energy regime, in Higgs inflation, we have that our inflationary time will happen at an energy that is higher than this cutoff. So this theory, this model here, is not trustable. You cannot trust in the predictions that it makes for the inflationary parameter. But it's not a bad model. We have just to make some adjustments in this model in order to be concise. We can think in alternatives, such as, well, maybe not the Higgs is the Inflaton, but as we saw in the type 1 and type 2 Seesaw mechanism, we can include new scalars to the standard model. So let's think, for example, a singlet extension of the standard model. This singlet could be the Inflaton, right? So the same thing would happen. We have to couple the singlet to the rich scalar, and we would obtain the same predictions, or at least something almost equal. But still, we would have to fulfill this constraint here. In order to preserve unitarity, we would ask that this non-minimal coupling is smaller than 1. As a result, we would have a non-minimal quartic coupling that is really small, let's say of the order 10 to minus 10. This is a problem because this have a correlation with the singlet mass. So the new field would have a really suppressed mass. And when we just said that at the end of inflation, we would have to reheat the universe. So if the singlet have a small mass, we wouldn't have reheating at all, and the universe would never enter the Big Bang stage, the radiative dominated stage of the universe. And it is a problem, right? But there is another alternative. We can think a triplet, to add a triplet into the standard model, in order to manage to do inflation in this kind of model. The triplet have an advantage. Let's imagine that we add this triplet in the standard model. So this is a general scalar potential, and as we have a triplet, we would get this trilinear term here at the scalar potential. This trilinear term would give a contribution to the mass of this triplet. So basically, this would be the mass. Here we have the contribution that comes from the quartic term and the contribution that comes from the trilinear term. So inflation is still bound this coupling to be small. But now we have another contribution that prevents this scalar to be much light. So basically, the reheating process is saved in this kind of model. So, okay, let's try to manage to build an inflationary model with a triplet scalar. And you do that, for that quest, we choose the Bimanuzel extension of the standard model. Why? Basically because we can attack many problems in that framework, as we see just in a moment. And in order to attack this problem, we introduce, here we have the standard model particle content, and we add to that, of course, a triplet under the SU2 symmetry. When this triplet gets a VEV, we will trigger the type 2 seesaw mechanism. Okay, this is at low energies, and at high energies, we will produce an inflationary time that is triggered by a non-minimal coupling between this triplet and the rich scalar. We also add to the standard model 3 right-handed neutrinos. Why we do that? Because we have to. As we know, if you introduce a new abelian symmetry to the standard model, we have to deal with anomalies. And so we introduce these right-handed neutrinos to conceal these anomalies. And also we introduce a new singlet field in order to generate the lepton number breaking at high energies that trigger that make possible to have a VEV to this component here and trigger the type 2 seesaw mechanism. Basically, this is the Yukawa-Lagrangian of our model. Of course, we have the other terms related to the standard physics. Here, we have the term that allow standard neutrino masses. Of course, when this triplet gets a VEV, we have masses to the active neutrinos, and this mass goes like this. So, to have a small neutrino mass, we have to allow a small VEV to this triplet. And as we see here, this is the potential scalar potential. And when we do the minimum conditions to this scalar potential, we obtain this oversimplified VEV expression. But I did this just to show you that the triplet VEV get this form. So basically, if we allow this mass parameter here to be high, we have, of course, a tiny triplet VEV. Here we have the singlet VEV. If the singlet VEV occurs at high energies, we have a canonical type 2 seesaw mechanism. If we have a small singlet VEV, we will have a kind of inverse type 2 mechanism. But either way, we can manage this mass scale here to obtain small neutrino masses. So basically, the mass of neutrinos is guaranteed in this kind of model. But as we introduce new right-handed fermions, and in the type 2 seesaw mechanism, we don't need that these fermions, these standard singlet fermions, get mixture with the standard model. We have the lattice state of these new fermions are stable. So we can investigate if it is a good candidate to dark matter. And actually, Antonio did some nice figures to investigate these, and we discovered that actually it is a good candidate to imp dark matter. Here we have one of these nice pictures from Antonio, where we have the cross section of this WIMP candidate. Here we have the mass, and here we have the angle of mixture between the singlet and the Higgs field. Those are some exclusion limits that come from Lux and the Xenon. This pink region, I think this is excluded by LAP. Antonio may talk later about a little about it. And this black region here are the dots that allows a 125 Higgs mass, right? This is basically this study was because the mass of this right-handed neutrino come almost exclusively from the singlet field, and this singlet mixture with the Higgs field. So we have to take care to preserve the mass of the Higgs, the measured mass of the Higgs. So that covered the low energy physics of the model, the low energy phenomenology. We have the mass of the neutrinos, just a summary. We have the mass of the neutrinos, and we have a dark matter candidate. But what about inflation? Well, at high energies, this is the potential calculated in the Georgia frame. See here that we have the radiative correction, right? And when we rescale the metric, this is a standard procedure, right? We rescale the metric in order to obtain the potential in the Einstein frame. We use this Einstein frame potential in order to calculate the predicted values to the observable. So this is the potential that we use to calculate the predictions for inflationary parameters. See here that we have the radiative correction that comes from the interaction in the Seesaw mechanism. And just in the denominator, we have the effect of the non-minimal coupling. At high energies, we can see that this term dominates, and the potential gets a plateau. So we have a flat direction, and we can actually perform inflation in this kind of mechanism. This is done by the slow roll analysis. Basically, these two parameters here quantify the amount of inflation. So we can see that inflation happens as long as these parameters here is smaller than 1. We have the number of folds, that is how much inflation happened in the beginning of the universe. Planck predicts it to be around 60. So it's an important parameter. And here is how we quantify the predictions to the prediction to the observed parameters, or the inflationary parameters that Planck measured to be in these values. Here we have the spectral index, the intensity to scalar ratio, and here, this is an important one, is the amplitude of the scalar perturbations. So when you do all these calculations, this is what we obtain. So note that we demand that the non-minimal coupling is smaller than 1 in order to preserve the unitarity of the model. Okay, so we have no problem with unitarity. And here we have the predictions to vary in the number of folds. As we can see, we have no problem to describe the Planck results. So the first goal of this work is done. We actually can describe the Planck results. The second is if we can constrain the parameter region, the parameter related to the Seesaw mechanism. And actually, when we demand that the amplitude of scalar perturbation is in that order of magnitude, we obtain a prediction related to the Yukawa coupling of the Inflaton to the standard neutrinos. Remember that this coupling is related to the mass of the standard neutrino. Of course, this is built under some oversimplified assumption. What are these assumptions? We assume that this Yukawa matrix is degenerated and is diagonal. To get a more precise prediction, we have to consider the entire structure of the PMNS matrix. But just to start, we see that we can actually use this parameter measured by Planck to constrain the parameter region the parameter space of this type 2 seesaw mechanism. So this is a great result that you obtain in this article. In addition, we have a model that is able to explain the Planck results to the spectral index and the tensor to scalar ratio. We've done that conserving the unitary, that is an important point, and also we obtain a dark matter candidate that is viable. So we managed to attack 3 problems with a model, and this is basically our main results. And that's all. Thank you.
Sorry, I don't know even if my question makes sense or not, because I don't know if I understood correctly what you said. But could you please come back on the